Now the first question we're going to do is this one, like x squared plus 3x minus 1 divided by x minus 1 whole thing squared. No, to the power 5, not squared. So anyone who knows basics of partial fractions and but does not know how to do this special case might end up writing this as, using the partial fractions knowledge, a of x minus 1 plus b of x minus 1 whole thing squared, c of x minus 1 cube, and you might stop right here and like start getting angry with the person who gave the question, d of x minus 1 to the power 4 plus e over x minus 1 to the power 5, which is actually correct if you write it like this, because here the numerator has order 2, denominator has order 5, so there's no need to add anything to them, and we have a linear factor repeating in the denominator. So when linear factor repeats, this is how we do it. And why we put a constant in the numerator is because we are dealing with a linear factor, so we need to have a constant in the numerator. So now the problem here is, when you try to solve this, you will multiply the left hand side and the right hand side by x minus 1 to the power 5. Then you will end up getting something like this: x squared 3x minus 1 equals, this one will become a times x minus 1 to the power 4, because one of the x minus y1s cancels, and then here 2 of them would cancel, here 3 of them would cancel, only 1 of them would cancel, 4 of them would cancel, and the last term would just be e. Now, like I mentioned earlier, the problem here is, although this is correct, it's very difficult to find a, b, c, d, and e. If you think of substituting x equals 1 here, it's only going to give you the value for e, and I think I have mentioned this in other videos too, that if the question was given like this, you are not actually allowed to substitute x equals 1, because this thing does not exist when x is equal to 1, because it makes the denominator 0. So it's like kind of mathematically wrong if you're talking about a scenario where x is never going to be 1, but to find things out, you're putting x equals 1. So basically you are at a scenario where x is not equal to 1, but you consider x equals 1 to get to the answer. So it is actually mathematically wrong for you to do that. But if you compare coefficients or substitute any other values, you are able to get some equations using a, b, c, d, and e. Then if you solve them, you will get the actual answer. But there's an easy way to do this. The way to do this is put a substitute as, say, let y is equal to x minus 1. What this does is, now we can rewrite x as y plus 1. And if you substitute now, you're going to get, instead of x, I'm going to put y minus 1 whole thing squared plus 3 times y plus 1 minus 1 divided by, our x minus 1 was y, so this is going to be y to the power 5. Now if I expand the numerators terms, this is y squared plus 2y plus 1 plus 3y plus 3 minus 1 divided by y to the power 5, and this is going to give us y squared plus 5y plus 3 divided by y to the power 5. Now if I separately divide, look what happens. I get a y squared over y to the power 5, 5y over y to the power 5, 3 over y to the power 5, which is going to be 1 over y to the power 3, 5 over y to the power 4, plus 3 over y to the power 5. Now if I backward substitute, I have my answer. So it's y is equal to x minus 1 plus 5 over x minus 1 to the power 4 plus 3 over x minus 1 to the power 5. So this is our partial fractions that we were looking for, where we had x squared minus 3x plus 1, sorry, plus 3x minus 1 divided by x minus 1 whole thing to the power 5. So what actually happened was we found an easy way to get to our a's, b's and c's and d's and e's. So by not writing in this way, but using a substitute and like changing the way the problem is. Okay, now if we did it using this ABCDE method, what our answer suggests is that we're going to get A is equal to 1 and B and C are going to be 0 and D was going to be D is going to be 5 and E is going to be 3. Okay, but we got it without writing it that way, but we finally have our answer in the way we want to get it, but we didn't go through the basic way of writing partial fractions and simplifying it. Right, this is our question number 1. Let's go to question number 1. There are other weird questions. So this is my question number 1. And now we have another special question. Okay, question number 2. Right, question number 2, I'm going to give you something like this. X squared plus 3, it's been divided by x squared plus 1 and x squared plus 2. Right, now if someone tried to apply the partial fractions knowledge straight away without like being careful, that person might think, okay, look at the numerator, I have order 2, look at the denominator, I have order 4. So okay, I'm not going to add anything, any polynomial to the answer, but I'm going to write the answer as x squared plus 1. Okay, it's a quadratic thing, so I'm going to put a linear term up there, and there's another quadratic term down there, and I'm going to put a cx plus d here. And you will do some simplification and try to find a, b, c, d. Okay, but if you look carefully, the question does not have any x's in it. It only have x squares, right? So if I consider all of these x squares as a single new variable like y, then you see I can rewrite the question as y plus 3, y plus 1, y plus 2, which I can easily do by writing it like this, or any other easy method. It's going to end up getting there. Now once I figure out a and b, okay, then I'm going to backward substitute. Right, this is find a, b, then you rewrite it x squared plus 2. You see, this is going to be the answer. Okay, I'm not going to find a and b. Okay, maybe I will find a and b using a easy method. What is it going to be? If minus 1, that's a 2 over 1. No, that's basically 2. And b is going to be 1 over minus 1, so that's going to be a minus 1, right? So final answer is going to be 2 here, a minus sign, and a 1 here. So look at this. This is interesting, because now if we did it this way and got a, b, c, d, what's going to happen is a is going to be 0, b is going to be 2, c is going to be 0 again, and d is going to be minus 1. But again, like in the previous question, without writing it like this, we got to the answer. Okay, this is the second special question I want to talk about. Now, the third one. Third one is a little different one. Okay, now something like this. Let's say you have x minus 1 whole thing squared and x plus 2 maybe, right? And you want to do it, and you will usually write it like this: a over x plus 2 plus some b over x minus 1, since x minus 1 is linear and repeating, so you will have to add this term too. But remember, although we are having a quadratic term in the denominator, you're not going to add a cx plus d. You're not going to do this. You're going to have a constant in the numerator, because the one that's, although quadratic in the denominator, that quadratic one is some linear factors square. So you're not going to look at that quadratic nature. All right. Now, I'm pretty sure that you are able to simplify this and get ABC. But what if this one was a 3? Then you will end up getting a d over x minus 1, 3. Okay? So this keeps adding new terms here, new constants here. So is there an easy way to do this? That's the question we have. Now, I'll not go into the x minus 1 to the power cube scenario. I'll stick to the x minus 1 square scenario. So we are going to use a technique called repeated application. Okay, this doesn't have a name. The technique doesn't have a name. I just gave it a name. So basically, we can repeatedly apply a concept, a simple concept, and get the complex version. Okay, without straight away solving the complex version. Let me show you how it is done. Okay, instead of looking at this, let's make it easy. Let's put y equals x minus 1 and say z equals x plus 2. Let's rephrase the problem. The problem that we have is 1 over y squared, is it? Okay, I'm going to look at this first. I'm going to look at 1 over y z first, right? 1 over y z is actually 1 over x minus 1 x plus 2, which you can easily do a over x minus 1, which is y, plus b over x plus 2. Now remember, these are not the ab's that we discuss here, so let's put something like lambda and mu. Okay, now that's our y is 1 over y z. Now look at what I'm going to do to the question. So what I have here is y squared z. I'm going to rewrite this as 1 over y, 1 over y z. So now my 1 over y z I know how to write. It's lambda over y plus mu over z. Now simplify. Okay, I'll put it here and simplify. 1 over y, 1 over y times lambda over y, that's going to be lambda over y squared, plus mu over yz. Now again, you see, if I take the mu out, I have 1 over yz. 1 over yz is lambda over y plus mu over z. So our final answer is going to be 1 over y squared mu lambda over y plus mu squared over z. You see? Now if I backward substitute, I get a lambda over x minus 1 whole thing squared plus lambda mu over x minus 1 plus mu squared over z. So look at this. So if I write it in this ABC form and found out A, B, and C, our C is going to be equal to the lambda here, and our B is going to be equal to lambda mu, and A is going to be equal to mu squared. So like we did in the first question, did we do? No, not the first question. So you have to be able to find lambda mu easily. You have to be able to find lambda mu easily with whatever the technique you have, or just by writing it in the basic way and cross multiplying, comparing coefficients or substituting values, whatever the method you want to do it. Find lambda mu, then you have the final answer. Now imagine that the earlier question I modified. If the question was something like this, So this means our new language is y cube z. Look at it. I'm going to take the y squared out and rewrite this. So 1 over y squared, this is going to be lambda over y plus mu over z. And it's going to be a lambda over y cube plus mu over y squared z. And you can keep on doing this by taking a y out, mu over y out, and 1 over yz, substitute, Or we could do, since we have already found 1 over y squared z here in the previous question, not in the same question a little while ago, I can just substitute what I figured out. So it's a lambda over x minus 1 whole thing squared plus a lambda mu over x minus 1 plus a mu squared over z. So if I simplify, I get a lambda over y squared plus, or why did I put x minus 1? So this is, oh, I have messed it up. Right, I have put z here. This is going to be x plus 2. Right, let's put the y z version. So this is going to be y squared, y, and z. So upon simplification, you get lambda mu over, I think I'm making a lot of mistakes. This is going to be y cube, right? Lambda mu squared over y plus mu cube over z. So again, if I backward substitute, I will get the answer. But observe this, the nature of it. So you see the y is the repeating one, which has a cube, x minus 1 cube. So in there, you have this lambda. But the lambda keeps repeating in the terms that involves with y. But the y cube has lambda, y square has lambda, and the mu. Mu being the constant that we had over z in our 1 over y z form. Then the other one has a mu cube, you see, and the one that only involves the z does not have any lambda in it. It has the mu cube. Right? So try to come up with the form that you could get in this scenario. So we can kind of guess what's going to happen. So it's going to have x minus 1 to the power n term, which has just a lambda up there. And it's going to be a lambda mu, x minus 1, drop the power. It's going to be a lambda mu squared, drop the power further. This is no use doing it like this, like it's too complex. But at the end, it's going to end up at a place where you have a lambda mu n minus 1 divided by just x minus 1. Okay, if you look carefully, you will understand this. Then we're going to have a mu raised to the power n divided by x plus 2. Right? Try to carefully look at this and see if this actually works. And try to understand why this is n minus 1. If you look at this, you will understand it, because when I am dealing with the cube, this was just 2. Right? So since I'm dealing with the power of n here, I have to have n minus 1 there. So this is not a must to understand, but like I'm just showing you that you can understand it if you look at the shape each of these questions have. So this is repeated application of something, one of these ideas. So you repeatedly apply this part, right? This part actually. You keep repeatedly applying it, and you get to the answer. And in questions like these, you can like initiate the question like this and get to this step, and later go back and find lambda mu and substitute here. You don't have to find lambda mu in here and then start working out with those same lambdas and mu's. Imagine lambda was -1 and mu was 3, then you put -1 and 3 here and keep simplifying. Then in case that your lambdas and mu's were wrong, then you will have to say you figured it out and later you corrected it, then you'll have to correct all of these steps. But if you do it this way, in case you figured out lambda and mu are wrong, you just have to correct the answer that you write after this step, because with those lambdas and mu's up to here you don't have to correct it. So it's better to do it in this way or using symbols. And these are 3 questions I wanted to discuss, and I hope you have learned something. So this is the end of video. We will meet in a different video. Okay.